Hello. This video is meant to be a quick introduction to permutations, illustrating how permutations can be connected with symmetries of a geometric figure. The example we're going to use is the regular pentagon. And if you go to this applet, it illustrates how two fundamental operations of symmetry can be used to reach any possible configuration of the vertices in the pentagon. For example, one basic, fundamental symmetry is rotational symmetry by a fifth of a turn. And if you do that, the vertices that starting at 1 through 5, starting with 1 at the top, get rotated so that 1 is moved to where 2 was, 2 to where 3 was, and so on. This can be viewed as a function where the image, one interpretation is the image of 1, or what was in the 1 position, what is in the position 1 was in, is 5. So the image of 1 is 5. The image of 2 is 1, and so on. A second symmetry operation, is going back to the original configuration, is a flip along the vertical axis of symmetry, passing through vertex number 1. Perform that flip, and 2 and 5 are switched, 3 and 4 are switched. So the function that leaves 1 fixed maps 2 to 5 and 5 to 2, 3 to 4 and 4 to 3 is another function. The set of all symmetry operations attaining the various configurations forms a group. And we'll see that this group can be realized not only as a set of physical motions, but also as a set of functions. Let's go back to Mathematica and talk about functions. The group of all permutations on the set of numbers 1 through n is denoted Sn. And as an example, here I'm going to look at a couple of functions in S4. I'm going to start with a function defined in matrix form here, where the images of 1, 2, 3, and 4 are listed below the numbers 1, 2, 3, and 4. So below 1 we'll have f of 1, 2, f of 2, and so on. So here's the definition of the function right here. The image of 1 is 2, f of 1 is 2, f of 2 is 3, and so on. F of 3 is 4, and f of 4 is 1. So that completely defines a function on the set 1, 2, 3, 4. Here's a second function, g, where the image of 1 is 3, 2 is 4, 3 is 1, and 4 is 2. Now this notation you may or may not find convenient, but it turns out there's a better notation that makes the structure of the function easier to see, and that's cycle notation. To convert to cycle notation, if we start with f, you observe that since the image of 1 is 2, we can describe what happens to 1, what the image of 1 is, by listing 1, and then what follows is its image. And then what follows 2 is going to be the image of 2. F of 2 is 3. Then f of 3 is 4. So 1, 2, 3, 4. And then f of 4 is 1. So we close off this cycle, and it's presumed that each element is the image of each element is what follows it, and the image of 4, the last number, is the first number. And this is called a cycle of length 4. All the elements happen to be involved in that cycle. The second function, g, is a little bit different. Here the image of 1 is 3, but then the image of 3 is 1, so that's a 2 cycle. That's closed off. And then we look at 2. 2 has image 4, and 4 has image 2. So g is a product of 2 transpositions, permutations of length 2, or cycles of length 2, whereas f is a cycle of length 4. Now, any two functions defined on the set 1, 2, 3, 4 can be composed, and if you apply the definition of function composition, it turns out that the composition of f with g is this single cycle also. It's 1, 4, 3, 2. Now there are a total of, in the case of n equals 4, there are 24 different permutations on the numbers 1 through 4. And so Sn is a group with 24 elements. And it's sort of it's one of the fundamental groups in group theory. I'm going to turn to a couple of subgroups that'll appear in Sn. First is An, the alternating group on n letters. And whether or not a permutation belongs to An is dependent on how many transpositions are needed to represent it. For example, if we look at the 4 cycle 1, 2, 3, 4 in S4, it turns out we can rewrite this as a product of 3 transpositions: 1, 4, 1, 3, 1, 2. Now, it turns out that every function, every permutation, can be written either as an odd number of transpositions, as a product of an odd number, or as an even number, but never both. So we classify a permutation as being odd if it can be written as an odd number, as a product of an odd number of transpositions, and even if it can be written as an even number of transpositions, product of those. In this case, f being odd is not in An, whereas G, if we go back to G, recall G is this permutation. Notice its structure is already a product of 2 transpositions, and so therefore G belongs to An. It'll turn out, we'll see that An will have exactly 1/2 the elements Sn has. So since S4 has 24 elements, A4 has half that, 12 elements. Another subgroup of Sn is Dn, and that's a group that can be realized or described in 2 different ways. D5 is the permutations, the group of permutations of the pentagon, the regular pentagon. And in general, Dn is the group of symmetries of a regular n-gon. And for each n, there'll be exactly 2n such elements. D5, as we saw in this applet, we can locate 1 in one of 5 positions here. There are 5 different locations 1 can be in, and we can either flip the pentagon, or not flip it, which means there are going to be 10 different ways that the 1 can be both located and the rest of the pentagon can be oriented. So there are 10 elements, and we can generate every one of the possible locations by a combination of a rotation and a flip. And the rotation can be described here. The image of 1 is 5, 5 is 4, 4 is 3, and 3 is 2. That's a mistake. Okay, so this 5 cycle, and the transpositions, the product of 2 transpositions, where 2 and 5 are switched, and 2 and 5, these 2 are switched by the flip, and 3 and 4 are switched. Okay, so by combining these 2, we get a subgroup, and it's essentially D5. There are other sets of permutations that can do that. Another one is this one here. It's a little bit more regular in its form. And all these issues are discussed in section 15.3.